Um, Today we're going to start on chapter 2. We're probably going to do about half of it. So we're not going to be the full period today, but there's something else for you guys to work on. I hope that you've checked your email and stuff, and you realize that the first extra credit is now online on Blackboard. All right, now this is worth 10 points. You have unlimited attempts at it. It's 10 questions. Basically, this is designed to make sure you can get into Blackboard, make sure that you know how to answer these types of questions, and to make sure that you start off with a good free 10 points, okay? Let's just take a look at what the questions are going to look like. Some of the questions are going to look like. Remember, everybody gets a unique quiz. If you take this 10 times, you will get 10 different sets of questions, 10 different quizzes, etc. Sometimes you'll get a question repeating, but not often. The questions on Blackboard will look something like this. This one is based on the tutorial for atomic configuration, where you have symbol, have to put in protons, charge, electrons, neutrons, whatever. When you look at a question like this, you obviously need a periodic table of some sort. There's one. There's also one on the Blackboard site. So on course materials, there's a new link down there. It's just a PDF file. You can print it and keep it among your treasured things. Okay? All right, well, here we're looking at SB. SB is antimony, of course. And we look at our periodic table, and there it is down here at the bottom. Its atomic number is 51. So, I'm sorry? Its atomic number is 51. So that means that it's going to have 51 protons. We are given that it has a charge of 0 and a mass number of 123. Number of electrons, since the charge is 0, must equal protons. And finally, if we know mass number and we know protons, we simply subtract these to get the number of neutrons. Now, Blackboard will not tell you that is correct, like the tutorial does. You won't know that until you finish. These types of questions that are based on tutorial have feedback. So if you get it wrong, it will explain to you what happened. Okay? Yeah?
Why is the charge 0 again? Why is the charge 0?
Why is it charge 0? Because we have the same number of protons, 51 positives and 51 negatives. Sulfur. Sulfur is going to be here in group 6, and its atomic number is 16. Okay? That means it's going to have 16 protons. Just type in 16. We are told that we have 16 electrons. Therefore, the charge must be 0. You must put a 0 in. And finally, if this is our mass number, and we have 16 of them as protons, we also have 16 neutrons. Yeah?
So the periodic table won't be on the plane, like you have it in the first one, it's not at the bottom?
Nope, not on Blackboard. You have to print it. It'll look like this, except small. And just, keep it with you all the time. Another one like this is aluminum. we are given the number of electrons and the number of neutrons. Aluminum is going to be right here in group 3, and it has an atomic number of 13. So that means it's going to have 13 protons. If it has 13 protons and 14 neutrons, its mass number is going to be 27. If it has 10 electrons and 13 protons, it's going to be a +3. But do not enter a plus sign. Okay, on Blackboard, do not enter the plus sign. If it's a minus, you must enter the minus sign, no space. Okay? One more of these here, we're trying to find the symbol. We are told that we have 28 protons. That means the atomic number is 28. And that's nickel. When you type this in, make sure you do the capitalization properly. First letter is going to be uppercase, and then lowercase after that. Blackboard will not like it if you did it the other way. Okay? If we have 26 electrons and 28 protons, 28 positives, 26 negatives, we have a +2. Again, no positive sign. And the number of neutrons from the mass number is 30. All right. There are also questions on significant figures. With this particular type of question, all you have to do is enter the number of significant figures. Just simply enter the number. This is in scientific notation. We remember that in scientific notation, all of the numbers in the exponent are significant. The coefficient. Therefore, this guy has 5 significant figures. Oh my gosh, we have to do a calculation. Actually, for this one, we don't. This is multiplication. We remember that in multiplication and division, what we do is we look for the least significant number. The result must have as many significant figures as the least significant. So here we have 3. Here we also have 3. Therefore, our answer will have 3 significant figures. Another multiplication. Once again, multiplication and division. You look for the least significant number. This guy has 4, this one has 3, therefore 3 in your answer. Oh my gosh, now we have to do a calculation. Actually, you have to add these guys and then decide what the answer is. You enter the answer, the numbers, right in the little thing on Blackboard. Calculate the following. Well, we're just going to add these 2 numbers together. Use a calculator. Remember, we're looking for the number of digits after the decimal. Our calculator answer looks like this. Our first number has 5 digits after the decimal, but our second has none. Therefore, we have to round this to that. All right, electron configuration is on there too. Remember, for electron configuration, you also need to look at a periodic table. And here we're looking for magnesium. Magnesium is here in group 2, atomic number of 12, so right here. Well, if it's in the third period here, that means that electrons are, the first period is full, the second period is actually full, and we put 2 electrons into our third period. This is going to go in the 3s first, these are the 3 p's, but there won't be anything in there. You must enter a 0 if there are no electrons in a given shell, okay? So, our 1s is full, so that means 2 electrons. Our 2s is full, 2 more electrons. The 2p is full, this holds 6 electrons. The 3s, we have 1, 2, and the 3p here, we have none. If you don't enter the 0, Blackboard will mark it wrong. Let's do this again. For hydrogen, sometimes it comes up very simple. Hydrogen, of course, atomic number 1, right here. That means it has 1 electron, and it will be in the 1s orbital. That means that the 2s, 2p, 3s, 3p are all empty. But you have to put zeros. One more, let's do silicon. Again, you find it on the periodic table. Here it is, right below carbon. So it is in our third period once again. That means our first period is full, 2 electrons. Our second period is also full, so there'll be 2 electrons in the 2s. There will be 6 electrons in the 2p. Our 3s is also full. And we're over here on the 3p's. We have 1, 2 electrons. So it looks like that. Okay? Now again, you can take this thing over and over and over again. Blackboard is set to take your highest score. The one thing you need to remember though, if you start one of these tests, they're actually all on one page. Okay, so if you start one of these things and you get bored and decide, gee, I've got 9 points already, I'm not going to worry with it. Don't just quit. All right, go down to the bottom, somewhere down here. There's a save and submit. Click that. Otherwise, Blackboard gets upset with you and it will lock you out. Okay, don't ever just leave it hanging. This thing goes offline at 11:30 tonight. Don't wait till 11. And when it's gone, it really is gone. If you're sitting here working at 11:30 in the middle of the test and you're doing great, it's gone. Yeah?
You got knocked out, can you restart it again?
I can restart it.
So we have to email you?
Yes. Email me in a panic. First, try to restart it. See if it will do it.
Even at 10
Yeah. Even at, yeah. 10 o'clock, I don't know. All right. Let's move on then to chapter 2. Chapter 2 is not difficult at all. None of them are. In chapter 2, we're going to talk about substances, introduction to compounds, and things like that. Chapter 3, we can actually work with compounds. And then finally, in chapters 4 and 5, we're going to do some real chemistry. But this is just our background. If we speak of a pure substance, we're saying that it contains only one type of matter. Okay? This could be an element, or it could be a compound. We'll see what a compound looks like in a little bit. but it's all one thing if it's a pure substance. If we combine two or more pure substances, we get a mixture. Mixtures. Well, mixtures that have obvious differences in appearance are termed heterogeneous mixtures. Now, a classic example of a heterogeneous mixture is something like this. This is gravel. I actually took this picture myself on a beach in St. John. Had to go down there just to take this picture, you know. But this is obvious. It's a mixture. We have big rocks, we have little rocks, little bits of sand in there and everything. You can separate these by simple physical means. You can pick out all the red rocks, all the black rocks, whatever. The other type of mixture is called a homogeneous mixture. A homogeneous mixture you cannot separate by simple physical means. Example of that would be salt water. Here I took a beaker, filled it with water from the seashore there, and just let it evaporate. And as it evaporated, the water, there's still a little bit of water down at the bottom, but you see the salt is crusting up. Obviously, this is a mixture. But if you look at it, it's clear. You cannot just take this mixture and reach in and pick out the sodium chlorides from the waters. It is homogeneous. We also just refer to these as a simple solution. When we talk about, sorry?
Can you go back, please?
I think.
Can you move the picture?
I'm sorry?
Can you move the picture?
Oh, I don't know. Once again, in the book, all of these things are in mini print. Hopefully, the recording software is working today. This is the recording software that works better. I recorded chapter 1, and you can get it on Chemistry Online under lecture recordings, part 1 and part 2. It's a YouTube video. The advantage there is that you can move back and forth easily. Because it was not my first choice for recording software, it's a little bit gory. But I hope that today's will be less blurry. The slides are also online. All these guys, if you need to copy something down or review it, just go to chapter 2 and you can flip through the set. All right. We said last time, matter is defined as any substance that occupies space and has mass. The simplest type is an element where we have only one type of atom. A compound. A compound results when you take two different atoms and you combine them. We'll see that there are two ways we can make compounds. One, the elements are present at a fixed ratio only. And this one, this is methane, natural gas. This not only has a fixed ratio of carbon to hydrogen, but it has a fixed spatial geometry. All methane looks like this. In organic, we'll see that this is called a tetrahedron. The carbon is in the middle. All these bonds are the same and whatever. Methane, natural gas, is a compound. All right, let's just review that very quickly then. Here we have a rock. If I asked you, is this rock a pure substance? Well, you might look at it and say, yeah, it's pure rock. Simplest way to tell This is a thin section of the rock. And here, under a microscope, you can see it's actually an aggregate. Lots of little things squeezed together. Obviously, it's a mixture, isn't it? Gold bars. They all look different, don't they? But on the atomic level, they are all only the element gold. By definition, even though physically they look different, they are all the same thing, and it is a pure substance. Now this one is a little bit tricky, I suppose. This is ice water. If I give you this ice water as it is this a pure substance? No, it's got little lumps in it, doesn't it? You can separate them. But if we let the ice melt, it would all be water, wouldn't it? So it depends on when you get to it, I suppose. But as it sits, it is a heterogeneous mixture. One more here. Under a microscope, this is what table salt looks like. Table salt is sodium chloride. It's a compound. We'll call this an ionic compound in a little bit. Again, if you look at all these crystals, they're all different, aren't they? But on the atomic level, it's nothing but an array of sodium and chlorine atoms, continuous array. You'll note the way they pack together. That's why the crystals look cubic. Any questions? Very simple question. You probably won't see something this simple on an exam. Classify these guys as pure substance, heterogeneous, homogeneous, or an element. Well, air. Air is a mixture, isn't it? It has oxygen, nitrogen, carbon dioxide, and lots of other little gases in there. But you cannot simply and easily pick out the oxygens, can you? Therefore, this is C, a homogeneous mixture. Ground pepper. Well, think of ground pepper, lots of little flecks. This is an example of a heterogeneous mixture. We saw seawater. Assuming that the seawater is pure, it's salt dissolved in water, that is a homogeneous mixture. Sugar. Sugar is a chemical compound. It actually looks like this. This is sucrose, so regular table sugar. It has a 6-membered ring here attached to a 5-membered ring here. The reds are oxygens, the blacks are carbons, these are hydrogens. Every molecule of sugar has this same structure. It has free rotation around all these bonds. It's a very dynamic molecule, they all are, but they will all have the same spatial arrangement on average. Gasoline. Well, we know that when we go and buy gasoline that we get to choose the octane level, whatever. Octane is an organic hydrocarbon, and gasoline is a mixture of lots of different organic hydrocarbons. Octane has a very nice low boiling point. Because of that, it works well in a combustion engine. It is a solution, a homogeneous mixture. And finally, gravel from the beach. We know that it's just lots of little rocks. Any questions? We're going to define substances as having properties. There are two classes. One are going to be chemical properties, and one will be physical properties. Physical properties, basically what something looks like, what it tastes like, what it smells like, if it's shiny, if it's whatever. That's a simple physical property. In terms of something like water, simplest type of physical property is probably the physical state. Here we have a picture. We have ice coming off our fence here. This is water in the solid phase. If these were melting, we would have dripping. That would be liquid phase, whatever. We also have water in the atmosphere. That's in a gas phase. Those are our physical states. Now, physical states, solid, liquid, and gas, differ by the inherent energy of the particles making up the substance. We'll see in a solid, the particles don't have enough energy to move away from each other. So they just kind of sit there and shake. They're never still, but they just sit essentially in one place and vibrate. In a liquid, we have enough energy where we can slip and slide them over each other, but they cannot break apart from each other. They need more energy to do that. And finally, in a gas, we've given the particles enough energy that they can totally fly away from each other, bounce off things, bounce off each other. That's our gas phase. Solid, liquid, and gas. When we talk about transitions, solid has a definite shape and a definite volume. Liquids have a definite volume, but they take on the shape of whatever container you put them in. So here we have our solid sitting as a lump. Here we have a liquid. Again, it will take on the shape of our round bottom flask here. Gases have neither shape nor volume. They take on the shape and the volume of whatever container you put them in. Phase changes. If we have a solid, we can put in energy and we can melt it and make a liquid. If we have a liquid, we can take energy out of our substance, freeze it, and convert it back into a solid. We have melting for this process, freezing here. Boiling, we're going to go from the liquid phase to the gas phase. Once again, we're quite simply putting in enough energy so that we can move from here to here. That occurs at a given point called the boiling point. You can also go directly from the solid phase into the gas phase. In general chemistry, we talk a lot about phase changes and diagrams and stuff like that, but this is the process of sublimation. You go directly from a solid to a gas without going through a liquid phase. All right, this is a simple concept. Let's go ahead and just apply these things to a simple problem. This is bromine. Bromine's an element. It's a halogen. It's over there. At room temperature, it is a liquid. You can freeze it The liquid has a very high vapor pressure, which means that from the liquid we have lots of bromine in the gas phase above it. Okay, so this little vial was frozen. It's a little cup. There's solid bromine still in the bottom, liquid bromine here, and this red gas is bromine in the gas phase. Don't want to play with it, don't want to mess with it. Bromine is fairly toxic. All right, it has a melting point of minus 7.2, a boiling point of 58.8. Simple question. If we're at minus 20, what will be our physical state? The question is simple, really. We're at minus 20. That is below the freezing point, isn't it? Have to warm it up to minus 7 in order to melt it. So this is solid. If we're up at 80, well, we put in enough energy that we have gone past the boiling point, which means that we are in the gas phase. And if we're at minus 0.12 degrees centigrade, well, that is below the boiling point, isn't it? And it is above the melting point. So bromine here is a liquid. Now, this last one I put in because people sometimes have trouble with negative numbers and things like that. One way to think about all this is to imagine a number line. Again, these questions are so simple you probably won't see these on exams. But if we have a pure substance and we're 15 degrees above its boiling point, what's its phase? Yeah, what you want to do is just think about it like a number line, okay? You don't need to put numbers on it, really. But we know we're going to go from a solid to a liquid to a gas. There's our melting point, there's our boiling point. And we are told we're 15 degrees above the boiling point. So we're here somewhere. If we're above the boiling point, clearly it's a gas. Compound melts at 115, boils at 325 at room temperature, which is about 25 degrees centigrade. What is it? We are told our melting point is 115, our boiling point is 325, and we're at 25. But we're all the way down here, way in the solid range. Oh, more negative numbers. Substance melts at minus 45, boils at minus 4. We are at minus 36. Well, here's our melting point, minus 45. Here we are. There's our boiling point. This should be minus 4, sorry. And we are at minus 36, so we're below 0 here. We are in the liquid phase. Any questions on the concept? Not a difficult concept at all. All right, you know, when we were talking about solids, liquids, and gases and stuff like that, we had all these cute little movies. We talked about putting energy in order to do these transitions. The reason that you have to put energy in can be explained by what's known as the kinetic molecular theory. Kinetic molecular theory simply says that all particles, everything, has an inherent attraction for all other particles. Simplest way to think about it, remember buckyballs? I think they're illegal now, but they're little tiny magnets. The attractive force that holds these guys together, well, that's magnetism. But if you have a solid, you have different types of intermolecular forces, but the effect is the same. Things are held together in a lump. So, if we're dealing with a solid, like I said, we have attractive forces between all these particles. There isn't enough energy in the system for these particles to break free of each other. And so they just sit there and they shake. And they're never still. Everything is always moving. But they cannot break free of each other. This is due to the attractive forces. Now, if we take and we put energy in, we wind up with a liquid. This happens at the melting point, obviously. And what we've done is we have put in enough energy here that we can, perhaps bend these attractive forces. But we can't, the particles cannot break free of each other yet. So they can slip and slide all over each other. Now, why does this happen at a given temperature? Because every substance is going to have a unique set of attractive forces holding it together. And since these are unique for the compound you're dealing with, it takes a unique amount of energy to begin breaking them. So that's why you go from a solid to a liquid at a given temperature.
So that's also it's not like one only temperature, like 100 for boiling for all the elements. They
Nope.
have, that's why they have difference.
Everyone,
Because they're,
every compound, every element has a unique set of attractive forces,
that's why
and so they have unique boiling and melting points. When we're in the gas phase, we've finally done it. We've put in enough energy where they can totally break all the attractive forces, and they just fly apart from each other. Again, because every compound, every substance is unique, this transition happens at a different temperature for every substance. So solid, liquid, and gas go from one to the other at unique temperatures. But it all comes down to the attractive forces that are holding them together. Any questions on the concepts? To summarize, if we have a gas, as you saw in your little movie there, the particles are highly separated. They have lots of energy. Because there's so much space between the particles, so much space, you can take a gas and you can compress it, squeeze them closer together. That's why gases are compressible. Because they have enough energy to just keep flying off forever, they will take on the shape and volume of their container. They basically go until they hit the wall or something. Liquids, they're very closely spaced. Can't get it any closer. That means it is not compressible. Okay? Attractive forces are intermediate. They have a defined volume because we haven't broken them apart from each other. And again, they slip and slide and take on the shape of their container. And finally, a solid. A solid, attractive forces are stronger. atoms are in or particles are in a relatively fixed position, not compressible, and they have a defined shape. So those are the things that we need to remember about substances. Any questions? All right, let's move on to the concept of density. Density is simply mass per unit volume. Now, what we mean by mass per unit volume, here I have 1 cubic centimeter. It's a cube. That means it's 1 centimeter on a side. The units of this is centimeter times centimeter times centimeter, or cubic centimeter. In chemistry, when we're dealing with liquids especially, we also use milliliter, where 1 liter is 1,000 cubic centimeters. 1/1000th is our milliliter. Remember, milli stands for 10 to the minus 3. All right, if we have a substance like this, it's going to have a mass. We have to use grams or kilograms or something like that to express our mass. It also has a defined volume. Our volume expressed in cubic centimeters. This ratio is defined as density. Let's say we had gold. Here's our little picture of gold atoms. If we have exactly 1 cubic centimeter of gold and we weighed it, it would weigh in at 19.3 grams. Therefore, we could say the density of gold is simply its mass, 19.3, divided by its volume, which we said was 1 cubic centimeter, or 19.3. Again, the units are grams per cubic centimeter. Any questions? Well, let's just look at some common things and just look at their densities so that we're familiar with the range here. Water has a density of 0.996 grams per cubic centimeter. That's at 25 degrees. People often round this up and say that density of water is 1 gram per cubic centimeter. It's actually 1 at 4 degrees centigrade, not at room temperature, so it's slightly less. Mercury. Mercury is an element. It's down here in the periodic table. Hg is a symbol. It's a liquid at room temperature. It's fun to play with. Back when I was a child, we used to get mercury and play with it. You know, it was fun. Now we don't play with it anymore. You'll never get to play with it. That's because mercury gives off mercury vapor, which is a neurotoxin. So that explains what happened to our entire generation, right? It's also very dense, 13.5 grams per cubic centimeter. Sulfur, 1.96, about twice that of water. Iron is certainly more than water, but you'll note that it's less than mercury. Gases. Gases are obviously very less, much less than, say, water. Because of this, the density of gases is quite often given in grams per liter. Remember, a liter is 1,000 cubic centimeters, so it's 1/1000th of these numbers. But they're very, very small. If we do it this way, 0.17 grams per liter or 1.4 grams per liter. Helium is less. That's why helium balloons float. All right, you're going to see something here that you don't see every day. This gentleman is standing in front of this large pool of mercury, and he is holding a cannonball. What he's going to do is simply drop the cannonball into the mercury. And you'll note, by gosh, you don't see a cannonball floating every day, do you? Why does the cannonball float? Cannonball floats simply because iron is less dense than mercury. So you can actually stand on a puddle of mercury like this, and it will support you because you are even much less dense than iron. Kind of cute. Any questions? All right, let's do a real problem. If you want to pull out a calculator and play along, this is very good practice. We have 250 cubic centimeters of a gas. It has a mass of 0.45 grams. What is the density of our gas? Well, when you see a problem like this, you immediately think density is mass per unit volume. We know the volume, we know a mass. Therefore, all we have to do is calculate the ratio in order to get our density. Mass per unit volume looks like this in an equation. Here's our mass, 0.45 grams. Here's our volume, 250 cubic centimeters. All we have to do is a simple calculation. And our density is 0.0018 grams per cubic centimeter. How about significant figures? Did I do it right? We have two significant figures up top. We have no decimal points, so we have two significant figures in the bottom. We have two significant figures in our answer. Okay, here we have a rock. The rock has a mass of 43 grams. We have a cylinder here with 22.5 mils of water in it. We're going to drop the rock down in here. When we do, the level of the water is going to go up. Now, when it finally settles down, we see our new volume is 45.6. What is the density of our rock? This is the revelation that Archimedes had. Remember, the story is that Archimedes was asked to see if the king's crown was really made out of pure gold. Well, couldn't really do this without melting it down and checking the density, right? He apparently was taking a bath, sat down in the tub full of water, it filled and spilled over the edges, and he said, "Eureka!" Which means, I think I got it. All you have to do is drop the king's crown into a measuring vessel like we just did with our rock, see how much water is displaced, and calculate the density. All right, density is mass per unit volume. Our mass, well, we know that, it's 43 grams. Our volume is the amount of water that was displaced. Therefore, we started at 22, we wound up at 45.6. That difference gives us the volume of our water. Do our simple calculation. We have 43 grams. We have 23.1 mils. That's our difference. And our density is 1.86 grams per cubic centimeter. Now, I put these down here as well because quite often you'll see units written with negative exponents. If we have grams per cubic centimeter, that is the same as grams centimeter minus 3. Also remember, a cubic centimeter is the same as 1 milliliter. So we could also write this as milliliter minus 1. That's read as grams per milliliter. Any questions?
What's more common to use? Which is more common?
Well, we use them all. On exams, sometimes when we have complicated units, doing them like this doesn't work very well. Word processors are very good at doing exponents, and so you'll see a lot of them that way. All right, let's do another simple problem. Here we have ethanol. Ethanol is the alcohol of consumption, also called grain alcohol, whatever. In organic chemistry, this is named ethanol because it has 2 carbons, that's an eth, and it's an alcohol, that's the OH, so ethanol. Our density here is 0.79 grams per cubic centimeter. Our mass is 15 cubic centimeters. Oh, we want to know the mass of 15 cubic centimeters. Okay. We're going to use our simple algorithm to do this. Remember we did this, I said you could use it, well, we're going to use it again. I've referred to density as a simple ratio, haven't I? Grams per cubic centimeter is a ratio. Our given here is going to be our 15 cubic centimeters of ethanol. Here's our 15 cubic centimeters. Our ratio is simply our density, 0.79 grams in 1 cubic centimeter. And of course, we're trying to find the mass, which will be grams. Now remember the way we did this. We start off with our given. Going to multiply that by the ratio. The ratio must be set up so that the units of given are in the denominator. There's our given. Our ratio, once again, must have cubic centimeters in the denominator, which it does. So we can simply plug it in. Our cubic centimeters are going to cancel, and we're left with grams. All right, do our simple math here. 15 multiplied by 0.79 divided by 1 gives us 11.8 grams. All right, did I do this right? How about my significant figures? Well, this number has 4 significant figures, doesn't it? This number has 3 significant figures. How about the 1? One is an exact number. When you're doing significant figures, you need to distinguish between experimental numbers, measured numbers. Remember, that's where the arrow was. We measured that. 1 is an exact number. It's a definition. Grams per cubic centimeter. Because of that, exact numbers are not counted in determining significant figures. Now we'll see several examples, many examples, of exact numbers as we go through the course. But again, remember, they do not count in determining significant figures. All right, we saw the density of mercury was 13.546. What volume is occupied by 999 grams of mercury? Let's set this up using our algorithm. Actually, no. We won't use the algorithm here, sorry. We know that density is defined as mass per unit volume. We are given the density, we're given the mass, and all we have to do is solve for the volume. Now we could use our ratio here, but let's don't right now. And there's a reason that I don't want to, because I want to show you this. Density is mass per unit volume. We are looking for volume. So we need to solve this little algebraic thing here for V. When we do that, it looks like this. Mass divided by our density. All right. All we have to do now is simply plug the numbers in. We have 999 grams. Here's our density, 13.5 grams per cubic centimeter. You'll note that cubic centimeter here is in the denominator, but it's in the denominator of a denominator. That is, it's the reciprocal of a reciprocal. Remember, we could use the negative exponent. Whenever you have a number or a unit or something that is in the denominator of a denominator, grams would cancel, but the cubic centimeter goes up top. There we go. This is the math. Again, it's 1 over cubic centimeters. So it's the reciprocal of a reciprocal, and that's the whole number. We'll do this a lot. Remember, anytime you have something like this, a reciprocal of a reciprocal, it's going to come up top as a simple unit. So our math here is very simple. We're going to take 999 divided by 13.546, and we get 73.7 cubic centimeters. Our first number here has 5 significant figures, doesn't it? This one only has 3. That's division. Therefore, we have 3 significant figures in our answer. All right, here we have oil and water. We're going to call them liquid A and liquid B. We are given that liquid A has a density of 0.985 and liquid B has a density of 0.873. If we take and we mix these together, without knowing that you're dealing with oil and water, which one is going to float? Well, quite simply, the cannonball floated on the mercury, right? Because it had a lower density. So the one that has the lowest density is going to float. The fact that they float, that they separate like this, is what's called immiscible. That means that the two liquids do not mix. The reason they don't mix actually goes back to the intermolecular forces we were talking about. Intermolecular forces are linked with polarity. Water is a very polar molecule. Oil is a very nonpolar molecule. Because of that, they are incompatible with each other, and the oil floats on top of the water. Liquid B will rise to the top. It is our least dense substance. All right. Let's take a problem like this and solve it with our algorithm. This is kind of something that you would actually do in lab. Let's say that we were doing an experiment and we needed 2 grams exactly of acetone. Acetone is a liquid. It's actually the major ingredient in fingernail polish remover. Okay, very common solvent in the lab. Density of acetone is given as 0.791. What volume of acetone do you need? Now, why do you do this in lab? Well, because weighing it out would be a bother. But it's very easy to take a liquid and measure its volume. So it's a real life problem. Going to set this up as given times ratio. Look at the problem here. Decide what is given, decide what ratio you'll need, and set it up. Well, our given is the 2 grams. Our ratio is simply going to be our density, 0.79 grams per cubic centimeter. And of course, we're trying to find volume, that's cubic centimeters. So to set this up, we start off with our given. Our ratio must have the units gram in our denominator. Now, as we've written this, gram per cubic centimeter, gram is in the numerator, isn't it? But we're just going to flip it upside down, that's all. We can do that. When we flip this upside down, our grams will cancel, and we're left only with cubic centimeters. So once you've set the problem up, all you do is feed this to your calculator. 2 divided by 0.793, and we get 2.53 cubic centimeters. We have 3 significant figures here. We have 3 significant figures here. And our 1, of course, is an exact number. Any questions?
It was 791, not 793.
Oh, okay. Again, I make my slides myself. There'll be mistakes all the time. Sorry. Okay, what does this look like on an exam? That's what it looks like. Very quickly, let's do a handful of exam problems. We have a mass of 93 grams. We have a density of 1.46 gram per cubic centimeter. What's our volume? Well, we know by now that there are a couple ways we can do this. Let's just do it with our formula. Density is equal to mass divided by volume. Going to solve this for V. Here we plugged in our density. Here we plugged in our mass. Now we're going to solve here. When we do that, it turns out to be 93 divided by 1.46. Do our simple math, and we get 63.7 cubic centimeters. Our units here, I stuck in liters. Remember, liters, 1 liter is 1,000 cubic centimeters. So these have the same numbers, but this is equal to 63,000 cubic centimeters. Any questions? Shall we do another one? Of course. Liquid has a volume of 51.2, has a density of 1.45. What's the mass? Well, I'm going to set this one up using our algorithm, just to show we can do it both ways. In our problem, our given is going to be our 51.2. Our units here are milliliters, which are the same as cubic centimeters. This is going to be our ratio. I just changed this to cubic centimeters because they're the same thing. Cubic centimeters cancel, and we're left with grams. When we do our calculation here, 51.2 multiplied by 1.45. Oh, I also did it the other way. So let's just bear with me here. Here I plugged in to our simple density equation. Now I'm going to solve for mass, and I get 74.24 grams. If I multiply these, I should get the same thing. All right, which of these is the correct answer? Well, you're all tempted, of course, to do this one, but 3 significant figures, 3 significant figures, 3 significant figures. Right? That makes sense. What is the density in kilograms per mil? If we have a sample with a volume of 1.57 mils and a mass of 89 29 milligrams. Well, density, mass divided by volume, no problem there. We are given a mass and we are given a volume. But we plug this in, our density is going to be given in units of milligrams per milliliter, isn't it? We do our calculation. Turns out to be 5,687 milligrams per mil. We must convert that to kilograms per mil. All right, how are we going to do that? We're going to remember that milli is 10 to the minus 3, and kilo is 10 to the third. If we took our answer here, this is 5687 milligrams, that's 10 to the minus 3 grams. If we converted that to grams, we would get 5.68, correct? Simply a factor of 1,000. Now, kilo is 1,000 grams. So we have to divide this by 1,000, get this guy, and this is our answer. Now there's a tutorial that we'll go over next time that will talk about this in much more detail. But let's just go ahead and finish our exam questions, and we'll pick up with this on Monday. We're looking for the mass in milligrams of a 62.58 cubic centimeter sample, and our density here is now given in kilograms per mil. Well, mil and cubic centimeter are the same thing. That's no problem, right? But we're going to have to somehow change our kilograms back into milligrams. Take our basic equation, plug our numbers in. Going to solve for our mass here, and we get 0.068838 kilograms. Now the simple way to do this in your head is to say, okay, well, there are 1,000 kilograms in every gram, right? 1,000 grams in every kilogram. So if we have 0.06 kilograms, all we have to do is move our decimal over 3 places, and that will give us grams. Once we have grams, we're at 68 grams. We know that there are 1,000 milligrams in every gram, right? That's our ratio. So all we have to say is that this is 68,000 milligrams. Okay, what's our answer? Real test question. I wouldn't kid you. How many significant figures are we working with? 2. 2 significant figures. So we have to round this to 2 significant figures. 68,800 rounds to 6.9 times 10 to the 4. This rounds to 69,000 milligrams, which is 69 times 10 to the 4. It is not 6,900 milligrams, and these have way too many significant figures.